I will talk first about, well, here, do a little bit of intro, things that you've all probably seen, or some of you have probably seen in one form or another. But these are some motivations that I've run across over the years that I really like. And then get into radiance assimilations as it's applied to snow. Talk about some of the issues related to not just remote or radiance assimilation, but also just in general regarding microwave remote sensing of snow. And then spend a little bit of time talking about this second to last bullet, things that my own personal impression of what's sort of holding us back at the moment. Not official NASA gospel or anything like that, just my own impressions. And then I'll wrap up by talking a little bit about the future options, satellite missions and some other things that may or may not happen in the future. Okay, first I do need to make sure I'm talking about the same snow that some of you may be thinking of. First, I'm talking about seasonal snow. I'm not talking about ice sheets or snow on sea ice. I'm talking about snow on land. And also, I'm not talking about snow that is falling through the air. I'm talking about snow that's already on the ground. I know there's a lot of work related to precipitating snow also. All right. Why does anybody care about snow? I'm sure many of you have seen there's a picture here in the bottom corner that came out of a nature paper. The shaded or the red outlined areas indicate places where the runoff is more than 50% dominated by melted snow. And I think you can argue about where exactly the line should be drawn, but I think the really impressive facts that struck me when I first saw this were that 1 out of every 6 people on the planet depends on water from melted snow for drinking, agriculture, what have you. So it's obviously extremely important for a large, significant fraction of people in the world. It also plays a big role in just the economy in general. You see the statistic here about the quarter of the global gross domestic product. And then there are a couple other things that are worth keeping in mind. There's a little bullet down here in the corner that snow, of course, terrestrial snow is a storage element in the water cycle. It stores a lot of snow, or a lot of water. But it isn't terribly useful for folks that want to use it until it melts. So the arrival of this big water resource and its availability are separated by months, which is an interesting aspect of snow. If you were to zoom in on that previous map to particular places in the world, the 50% statistic becomes, or can become even more significant. And for example, in the western part of the U.S., it's something on the order of 80 to 90%. I'm sure lots of you are familiar with the climate out west. And I think the other important thing to note here is that so it turns out that a lot of the snow that falls in the U.S. happens to fall out there in the West, and that's probably a good thing for them. And if you're interested in trying to estimate how much snow water equivalent that represents, you've got sort of 2 basic approaches, if you will. One is to use models, and another one is to use satellite measurement. And I know these days there's some overlap between those, but for the moment, sort of think of them as different approaches to estimating how much snow water equivalent there is. I don't know if this number is still true, this 30% number. I know models have improved quite a lot, and I think the observations and measurements have also improved. But at least back in sort of around the time that we were putting together the story for why NASA should be interested in a dedicated snow remote sensing satellite, the best state-of-the-art model prediction and the best state-of-the-art satellite retrieval estimate couldn't agree closer than about 30%, which seemed pretty crummy. So this slide here shows, I guess the black curve is the national snow analysis that NOAA puts out, and the red curve is a satellite-derived product from the SSMI passive microwave instrument, and the green curve is the difference. So the 0 minus is here, sort of in the middle of this graph. And this is just for one northern hemisphere winter. Oops. Did that go away? And you can see that, at the beginning of the snow season, there's no snow, and then it builds up to a peak, and then it disappears towards the end of the snow season. But you can clearly see that there's a significant difference in these two so-called state-of-the-art ways of estimating how much snow there is over the entire continental U.S. Here's another picture, sort of using a color scale to show you intensity-wise where the difference is. So again, it's in this case, it's the Answer-E passive microwave instrument that was used compared to the NOAA model-based product. And what you're seeing plotted in the colors is the actual difference. And this box over here in the lower left puts if you were to integrate the difference over the whole continental U.S. and add up what that is, it's a little over 100 cubic kilometers of water on this particular day, just one day. It's a relatively impressive amount of water, 1/5 of the total annual flow of the Mississippi River, for example. That's the magnitude of our uncertainty, if you will, at least a few years ago. Again, things have undoubtedly gotten better.
Is that mostly related to uncertainty in the depth or extent?
Well, each of the two different methods, the model-based method and the satellite measurement method, both have their limitations. In the case of the satellite-derived method, there's saturation, and once you get above about 150 millimeters of SWE, the particular SWE retrieval algorithm that was used to make this plot saturates, so it cannot see SWE beyond about 150 millimeters. In the case of the model, it's all the usual things, all the usual limitations of the model. Another way of looking at the importance of snow, and this is put together by NOAA. So NOAA actually hired a real, honest-to-goodness economist, and as I always say when I show this slide, they had a card-carrying economist use standard, well-known economic techniques to come up with these numbers. So there's actual documentations you can cite having to do with the economic impact and importance of snow. The other aspect of snow is of course, natural hazards. The snow melts, and if it can't infiltrate into the soil, especially, for example, the soil happens to be frozen or it's already saturated, that's basically the definition of a flood. And so this is a timeline. Starts over here at the year 1900 and finishes over here at the year 2000. So during this century, it shows the pictures correspond to the 10 worst floods in the U.S. And then the little text next to each one shows you where the dollar estimate of the damage in 2002 equivalent dollars, and so forth. But I think for our purposes, the key thing here is that if you took the 20 top most significant floods during that century, 9 of them were snow-related. And it's usually the mechanism I just referred to. There was snow, there's some sort of early melt due to the weather conditions, and for one reason or another, the water couldn't go down, so it could only go horizontally. Another application for snow, especially on a global scale, of course, is looking for climatic changes. Snow happens to be one of the geophysical parameters for which we have a very long satellite record, going back to the 1960s. If you're talking about visible satellite measurements, and going back to the 70s if you're talking about microwave. And so, and by microwave here, I'm talking about passive microwave. So folks have stitched together all those years worth of satellite data for the entire northern hemisphere to look at snow extent. So what they're really interested in, what this red curve going up and down shows, is the growth of the snow-covered area and the shrinking when it melts in the summer, looking for climatic trends. And the interesting thing to note is that at least as far as this study was carried out, coming up to about 2006 or so, there was no statistically significant trend that they could detect when it comes to the maximum, the area maximum for each year. If you were to break this down and look at it in terms of the timing of the timing of when the snow cover started and when it shrank, then you would detect significant trends. But just on a sort of zeroth order basis, this data does not show a statistically significant change in the maximum of the snow cover. And obviously, with existing sensors and future sensors, this record will continue, and we'll see if that result changes or not. So the next several slides, I tried to summarize some of the advantages and disadvantages, pros and cons of microwave remote sensing with respect to snow. Some of these are pretty obvious. I think if you work in this field, water interacts very strongly with electromagnetic radiation. Microwaves are very suitable for looking at snow for various reasons. And here's some of the not so great features. Snow is very variable, and that obviously makes it more difficult, especially for most of that time period that I showed in that long time series. We've had passive microwave instruments in orbit. Once in a while you have a radar. Most of the ones up till now have not really been at wavelengths that are really great for looking at snow. So you're primarily talking about passive microwave sensors, and those, there's no getting around the laws of physics and the size of the antenna that you can put on a satellite. So the footprints tend to be relatively large. The other aspect of passive microwave sensing in general is that you're getting the brightness temperature number that you get is a path integrated quantity. So you could look at it in an image and say, aha, this pixel is 202 kelvins. Well, there's a lot of different snow packs and conditions that'll give you a 202 Kelvin number. It's not a unique one-to-one correspondence between a brightness temperature and a particular snow condition. So you need a lot more information than just the one number that you get from a satellite in order to really sort of decode what the conditions are on the ground. And I don't want to limit myself entirely to passive microwaves, although, as I said, most of the record, most of the work that's been done to date has been with passive microwave. Radar appears to have some good capabilities when it comes to snow remote sensing. And as I said, there have not been any dedicated snow satellites to date with radar, and people have used other satellite radar to try to do snow remote sensing, but again, the wavelengths weren't really very optimal. And the biggest attraction for radar, as it seems to be with everything else, is that if you use a synthetic aperture radar, you can get much, much better spatial resolution, at least in theory. The problem is that your noise also goes up. And so if you're dealing with a quantity like snow that's fairly noisy to begin with, yes, you'll get great spatial resolution with a SAR, but the noise associated with that, that single look, for example, would be pretty huge. So to deal with that, you tend to have to average, and that's not a unique thing. Most radar remote sensing involves, using multiple looks. But we've also found so far that not only do you have to average multiple looks, but sometimes you even have to start, increasing or averaging over multiple footprints in order to get to shrink the error bars. But I'd say within the last few years, there's been a fair amount of interest in seeing whether a combination of active and passive microwave sensing somehow give you the best of both worlds and give you ways of dealing with the limitations of both techniques. Okay, so some more pros and cons. Dry snow is relatively not absorbing microwaves. So that's not necessarily true for all things in all targets. Soil moisture, for example, wet soil is actually very absorbing. So it's a different electromagnetic problem, if you will. The character of the problem is different. So the fact that snow's not very absorbing means that microwaves will penetrate pretty far into a snowpack. It also means, on the other hand, that if you're looking for thin snow, you'll see right through it. And it's difficult to detect thin snow. So in fact, those estimates of snow-covered area, if you look at where the errors are the biggest, when and where tends to be where you have thin snow. For example, right around the edges of the the big snow mass that's sort of centered on the North Pole. When is also like at the beginning and the end of the snow season when the snow is really thin. So the biggest source of uncertainty in those long-term snow extent records is almost entirely correlated with where snow is thin, because that's when the passive microwave sensing has the hardest time detecting whether or not there's snow. And one approach to getting around that problem, which has been taken by several groups, is to then try to blend microwave and optical data. So this is a case where the optical sensors, if it's pretty easy to detect white versus non-white. You do have to deal with clouds and all these other things. So if you can figure out a way to deal with clouds and blend the optical with the microwave, you could conceivably have a way to deal with this particular source of it. All right, so the other implication of the fact that you're in a relatively non-absorbing electromagnetic regime is that the radiative transfer involved is primarily scattering dominated. It's not terribly, the scattering is much more important than the absorption. And so, for example, for passive microwave, let's say you have a bunch of snow sitting on the soil, at many of the common wavelengths that you would use, or that have proven to be useful for snow remote sensing, the signal is actually coming from the soil beneath the snow. The snow actually is just attenuating, scattering the signal. The more snow you have, the colder the brightness temperature. Your brightness temperature is actually coming in large part from the soil underneath the snow. So that's, for example, one of the ways that you have to deal with the fact that you're in this kind of electromagnetic regime. Now, wet snow is very different. As soon as you get a few % wetness in snow, it becomes very absorbing electromagnetically, and the microwave signature just changes completely. So it's very easy to detect that. You can see 100 Kelvin jumps in the signal. This is one of the easiest things to detect with microwave sensing. But if you have, so let's say that the top surface of your snowpack becomes wet, well then you can't, whatever's going on underneath it, you won't see. You suddenly just lose all information about what's going on there. If one of your lower layers or an intermediate layer in your snowpack is wet, you might be able to still get information about what's above it if that's dry, but then anything below the wet layer, forget it. So here's a couple of well-known snow experts during the NASA Colan field experiment back in about 10 years ago in Colorado. And the reason I show this picture is because, from the surface, qualitatively, it looks so uniform, it looks so homogeneous. Snow should be easy, right? Well, we've discovered that the stratigraphy, the layering of the natural snowpack, turns out to be have a very strong effect on the microwave signature. That's great if you're interested in layering. Usually we're not interested in layering, or at least we haven't gotten that sophisticated yet. So if you're just interested in what's the total depth or what's the total sweep, stratigraphy is something you'd really rather not have to deal with. And unfortunately, nature is not that kind to us. Not only that, but layering tends to come because of the simple fact that you tend not to get all your snow all at once in one snowfall, right? You'll get one snowstorm that comes through, you get a few centimeters, another, a few weeks go by, and you get another snowstorm, you get another layer, and so forth. So each, the layering tends to be closely tied to the weather history of that location. And in fact, big snowstorms. And what you'll find then is that in between, a little crust will develop on the top surface of a layer. So the snow falls, and then after that storm, there's a period of weeks before the next bunch of snow comes, and during that period of weeks, the top surface will develop a crust. It'll become a little denser. It might go all the way to an actual ice layer, or it may just become sort of like densified snow. And that is easily detectable by microwaves also. But obviously that's not changing your SWE or your depth by all that much, but it does change your microwave signal by quite a bit. So you've got to deal with those kinds of things. The way to deal with it, if you're trying to model it, is of course you need more fidelity in your model. You need more layers. You need a way to deal with history of the snowpack, because that's one of the ways that your model can predict when an ice layer will or will not form and what the density of that is. So that just means your model has to become that much more complicated or that much more sophisticated. And maybe for what you're trying to do, you can't afford the extra complexity. So again, here's a real snowpack out there. You can clearly see the layers. You can just imagine how this developed, right? There was a snowstorm and that much snow fell, and then there was some time in between before the snow on top came, and this little crust layer here formed. And then another snowstorm came, and you got this layer, and then you got another crust, and then finally, so just by looking at this, you can tell how many snowfalls there were. Very typically, or I would say all the time in models, you make simplifications. It's just a fact of life, right? One very common simplification is what you see on the left. Most snow physical models, especially the electromagnetic ones, will model the snow grains as spheres, because spheres are computationally convenient in electromagnetics. Some of the more sophisticated ones will actually let you change the size of the spheres as you go from the top of the snowpack to the bottom, but some of them won't even let you do that. If you actually take your personal electron microscope out in the field and look at real snow, what you see is over here on the right. So these are actually samples that were collected during that same field campaign and then taken over to Beltsville, the USDA, where one of the electron microscope lab folks over there liked snow. And so there's a whole website of these electron microscope pictures, including some stereo ones. You can get out your colored glasses and you can see beautiful 3D snow grains and everything. But the size scale for all of these is the same. So you can see the relative sizes of grains within the snowpack. And how you end up from snowflakes to all of these is part of what makes the microwave aspects of snow challenging but interesting.
Can you tell the wetness of the snow on the right hand side?
Sort of. I'll show you another picture of what wet snow looks like. Right, so scattering, as you can imagine, a lot of you may be familiar with scattering of things in the atmosphere, raindrops, snowflakes, or what have you. Scattering is very strongly controlled by the size of the scatterer relative to a wavelength, the shape and the orientation of the scatterer, and so forth. In most problems, and almost every other remote sensing problem involving radiative transfer, you're in a regime where you've got independent scatterers. So that means that your scatterers are far enough apart that you can consider the scattering around one of them independently of anything else. simplifies the computation drastically. Well, unfortunately in snowpacks, obviously your scatters are touching each other, so forget that. You're not in that regime at all. Of course, it didn't stop folks in the early days just applying the same independent scattering approaches as they were accustomed to. Now, the other thing is that you saw on the previous picture, some of the side, the shapes are pretty wild. Definitely not spheres. And if you actually wanted to try to compute or estimate the scattering off of one of those complicated shapes, it would be a pain. So I mentioned that conventional radiative transfer is not valid because you have what is considered to be a dense medium electromagnetically. And so the real theory behind dense medium radiative transfer is pretty nasty. It's, some very, very clever people have worked on it and gotten it to a point where it's all in papers and books, it's all in literature, there's even code that you can download now. And they've simplified it to the point where, there's the part that deals with the dense medium aspects, and then you take those and you plug them into, the equations for conventional radiative transfer. And after that, everything's the same as what you're accustomed to. And the last thing is that snow metamorphoses. That's how, of course, you get all those complicated shapes that I showed earlier. Now, those of you that may be studying precipitating snow are probably familiar with one of these diagrams that shows how you get all the different shapes of precipitating snow depending on where you are, with respect to the temperature and vapor pressure. Well, forget it. You don't have to worry about this when you're talking about snow on the ground. So here's a sort of a time sequence cartoon of what happens to snow. This is what it looks like, when it's falling. This is what it looks like shortly after it's hit the ground, and it very quickly turns into a blob. Right? And here's electron microscope pictures that show you what really happens. And this is representative of one of the main metamorphism types of metamorphism within snow. Right. The other thing is that density changes dramatically. So you can imagine, when snow first falls, it's really light, it's really fluffy. The density's, like 100 kilograms per cubic meter. It's very light stuff. Well, this experiment, somebody actually went out and measured the density. Snow water equivalent, assuming a density of that 100 kilograms per cubic meter, for each hour during a fresh snowfall. And the point of this is just that. Here's the depth increasing. It's over 9 hours. A total of 12 centimeters of snow fell, and this is the actual measured water equivalent. So of course, it goes up as the depth goes up. This is what you would have estimated if you had just assumed a fixed density during those 9 hours. And this is how much you would be off by making such a simple assumption. The whole point of this is just that even over the course of a few hours, the density can change pretty dramatically. Further, another way of looking at density is if you compare different types of snow. So I'm not talking about the first 9 hours of snow, but if you just compare all different kinds of snow, some of them have been out there for months. Very fresh snow, very light snow, as I said, the density is very low. This is typically what you get most places, most times. Other kinds, there are types of snow or conditions that produce much denser types of snow, wind crusts, so you need a nice hard layer on top, and you're up in 400, that's basically half or 40% of the way to liquid water, and then hard wind slab. And so, if any of you've been up in the Arctic, you can stand on this stuff. That'll support your weight. It's like concrete. Great stuff to make igloos out of. Okay, so the other metamorphism, type of metamorphism is constructive. And so this tends to happen when you have very strong temperature gradients within the snow and involves vapor diffusion. So what you have there is you're going from these sort of rather amorphous looking blobs to cups, geometric cups. And this is what depth hoar looks like. So if you actually went out and looked at snow or depth hoar type snow with a microscope magnifying, I mean, some of these are huge. These can be, easily several millimeters, and in some cases like almost up to a centimeter. You can see them without a magnifying glass. This is some interesting stuff that has been done in the last few years to show the metamorphism over time. They took a CAT scanner and modified it so that you could stick a snow sample in there. So you put a sample in that's about a cubic centimeter, and then it does very, very high resolution CAT scans, and you can differentiate between what's ice and what's air. And then they can, in the sample cell, they can impose a temperature gradient to force metamorphism at different rates. So here you can see where the ice was and the shape and the sort of distribution of ice versus air pores at the start, and they imposed a rather strong temperature gradient here, and then went about a month, and you can see what happened over that month. And things clumped together. So this, what you would expect with that kind of a temperature gradient here is this kind of metamorphism. The smaller grains getting bigger, clumping together and growing and getting bigger and bigger and ending up with angular sort of crystals. So anyway, this is an interesting technique that has really sort of only come out in the last few years. This is what snow looks like after there's been some melting and refreezing. So you can see where the grains are joined by refrozen water, and you get this kind of very characteristic looking condition. All right, so let me talk a little bit about radiance assimilation. I'm only going to show some examples related to point scale studies that I've done with the folks, or my colleagues, Mike Duran and Steve Margulis. Other folks have now, especially in the last couple of years, looked at more than just point scale. Some people have been looking at basin scale things and even some global scale work, but I'm not going to address that. A lot of that's still in review, so I think if you wait about a year, those papers will probably be out, and you'll see what other folks have been doing. So why would you even want to try radiance assimilation for snow? Well, I don't know why other people would want to do it. I got interested in it because in my other life working with atmospheric sounders, I talked to a lot of my NOAA NWP colleagues, and I found out that several years ago the NWP community switched to radiance assimilation, and they got this quantum improvement in their forecast skill. And so I thought, oh, well, I wonder if we could do that with snow. So just as this is not radiance assimilation quite yet, but this is kind of my simplistic cartoon of how snow retrievals were done before. This is the traditional way of doing things. You take your remote sensing observations, they go into some kind of what I call a snapshot retrieval, because all it uses is the observations from that one point in time, no other information. And then out come your SWE or depth estimates. And the advantages are, well, it's really simple. You don't need a lot of ancillary information. There are certainly limitations, like I mentioned, the saturation, the depth saturation. That's very well known. Forests and vegetation mask the snow signal. That's another very well known limitation, and so on. So one way of getting around, so this has been pursued, it's still being produced. So there's the official AMSRE snow product, for example, still uses this type of approach. And there are other operational snow retrieval products that still use this type of approach. But it's, my personal opinion is that we've kind of reached the point of diminishing returns. Yes, we have a forest fraction correction. Yes, we have instead of having fixed coefficients, one set of coefficients for all snow conditions worldwide, we've now broken it up so that it's regional and So folks have played around with being able to adjust the coefficients that are in the retrieval equations in order to match particular snow conditions. So we've sort of been able to tune it a little bit. Yeah, you'll get better results, but how much more can we play that game? It doesn't seem like you can keep playing that game. You can keep massaging it for the next significant figure, and I'm not sure that you're really going to be able to make any significant improvements.
Ed, are those instantaneous retrieval algorithms empirically based or analytically based?
Half and half.
Half and
Yeah. So anyway, as I mentioned before, I thought, well, let's try radiance assimilation. So what do you need in order to do radiance assimilation for snow? It's the same sort of things you need to do radiance assimilation for anything else. You need a physical model of the thing that your target of interest. So that would be a snowpack model in our case. And because snow sits on top of land, you're going to, in the case of snow, you're going to also need some model that gives you the land conditions, like the surface soil temperature, soil moisture, maybe. And then you need a radiance model. You need a radiative transfer model that will produce your predicted brightnesses. Compare those brightnesses with the actual observed brightnesses in an assimilation framework, which then goes in and magically knows which knobs to turn in here to make things agree better. That's sort of my simplistic view of how this works. And the advantages are that now you have something where it's all forward. These are all forward models, so you avoid issues having to do with inversion. And these can be physically based. They don't have to be, but you have that option available to you, which is nice, so that you can have consistent physics, if you will. And the obvious disadvantage is we need a whole lot more information to drive this model. And it's not clear that you actually have that information in all places when you need it. So, and then of course, this is all, these models are driven by weather forcing, so to some extent their skill is going to be a function of how big your driving forcing data is. All right, so how well does this work? That's not that hard to set up, but how well does it work? As I said, I will show a few slides to show some results from some point-based studies that I've done with some of my colleagues. And then there are these other studies that, as I say, will be probably published within the next year or so. When we first started out looking at this, I'll go back to this picture, I wanted to be very, very sure that at the end of our study, we could answer questions like, well, gee, it didn't work too well. Why is that? Which part of this was the thing that wasn't working well? I didn't want to just say, oh, well, I can put these together, feed it some data, turn the crank, output some numbers, and yeah, maybe it looks okay, or no, maybe it doesn't look that well. So what? I don't really learn much from that. I want to be able to know, how well should each one of these boxes, how good does this have to be? How good does this box have to be? How good does this box have to be? How good does this data have to be in order for this whole thing to work? And so my way of thinking about it, since I've got an engineering background, is to divide and conquer, to try and design experiments that will answer those questions, not just connect it all up, hit go, and see what happens. So we looked at, wanted to make sure that if we try something, we want to know, and it works, we want to know why it works. If we try something and it doesn't work, we want to know why it didn't work. And we want to actually come up with quantitative numbers. How good does that snow model have to be? How good does your radiance model have to be? And so forth. So we used data from, again, this cold land processing experiment back in 2002, 2003, and we focused on one particular point location called the local scale observation site, because at that location, that was the only location where we had coincident microwave observations with the detailed snow ground truth. And there's a pretty picture from the overall experiment. So here's that same block diagram, and these are the actual names of models and things that we use. So we used the version simple SID as our land surface model. We used a 3-layer snowpack model called SAST, and then our emission model, radiance model, was Reynolds. GBMR is the name of the microwave radiometer system, ground-based system that was giving us our observed radiances, and then the simulation framework we're using ensemble column filtering. And then the weather forcing was from dedicated instruments that were set up for at that site for this field experiment. So this is just a picture to show you what that microwave instrument looked like. Our Japanese colleagues brought this all the way from Japan. And this is a photo and an overhead diagram of the area. So the radiometer was sitting here and was sort of scanning around looking in this open area out here. And then at these little dots, we actually dug snow pits to do detailed snow ground truth. And the snow ground truth consisted of course, depth and density and temperature, but as a function of depth. So we took many samples as a function of depth. And then grain size is one of the most important parameters, and that was done using handheld magnifying glass, basically. So we were able, as a function of, so for 1 week, this is each one of these bars is for 1 day. These diagrams show the detailed stratigraphy that we observed in the snowpack. So you can see each block represents a layer. The numbers tell you the mean size of the snow, of the grains within the layers, and the blue shows where there were ice lens, where there's densified single layers. So this gives you an idea of the snow conditions there. And so in our first paper that we did in 2008, we didn't actually do full-blown radiance assimilation. This is more of an open loop test of how well can you model the brightness temperatures. So for 3 different frequencies, 18, 36, and 89 gigahertz over the course of the 1 week, the blue is vertical polarization, the red is horizontal polarization. And let's see. So the open circles are the measured value brightness temperatures, and the solid circles are the modeled brightness temperatures. So primarily interested in these upper 2 plots, the 18 and the 36 gigahertz. They do, in some cases, a reasonable job. At vertical pole, you tend to get a better match than at a horizontal pole here, and we later figured out why that was. We looked at 89, we computed 89, but then we didn't really focus much on that, so I'm not really going to go into that at all. Another thing we did was to look, again, as I mentioned, we wanted to understand what the key drivers were. And so we did a sensitivity analysis of which parameters within the snow model, density, temperature, size of the grains, and so on, were the biggest drivers, the most sensitive parameters that determine the brightness temperature. And then we quantify that, so we actually have these in quantitative terms. So this is kind of the in a nutshell, the results, but you notice, as I said, we wanted to come up with real numbers. So we sort of, it's a little subjective, but we decided let's compute these numbers for coming within plus or minus 5 kelvins of the model brightness temperature has to agree with the measured brightness temperature within 5 kelvins. In order to achieve that, how well do you have to know the various things? And these numbers are after update by assimilation. So you need to know the density to within 40 kilograms per square meter and so forth. So now we have an idea. This is in part an answer to the question of how good does that particular model or that block in my block diagram have to be. And if you do the assimilation, so we did radiance assimilation with respect to snow depth, and that's what's on the vertical axis here, and again the horizontal axis is that 1 week. This dotted line is the mean, and this shaded area is the ensemble, I guess. I don't claim to be a data assimilation expert, so Bart, maybe you can correct me if I use the wrong terms, but this is the ensemble of priors, and this is the ensemble of posteriors. So this is before radiance assimilation, this is after radiance assimilation, essentially. And the line down the center is the mean of each of those respective ensembles. So the ground truth, or the real truth, were these blue circles. those are measured, physically in the actual snowpack itself. So you can see that if you just used the model without any radiance assimilation, you would have been off by at least a factor of 2. And the assimilation was able to correct that, if you will, and bring you up a lot closer to the actual truth. And the red square, or the red X's, are the non-data assimilation estimate. So those come from that snapshot algorithm that I mentioned earlier, the traditional snapshot. Right, so Allie here, who came in and did some work at Goddard for a few months, and then also went back to finish up his PhD, did some work using the same electromagnetic model, but a different snowpack model. So whereas the model that we used for this study had 3 layers, Allie's model had 50 layers. So this was an experiment, if you will, to see how much better you might or might not be able to do if you increase the fidelity of your snowpack model by like an order of magnitude. And so again, you can see the different frequencies. Here we just have the 2, the 18, and the 36 gigahertz in the same 1-week period, and the 2 different polarizations. And you can see over here, these are sort of our initial results. Especially at the horizontal polarization, you see there's quite a bit of difference between the observed and the model brightness temperatures. And then Allie, stared at things for a while and realized that the Crocus model wasn't doing such a great job at modeling those ice layers, those dense snow layers. And that electromagnetically is, a horizontal pole is much more sensitive to ice layers because it's a dielectric boundary. And so when we adjusted the density of those layers, we could get much better agreement for the horizontal polarization, whereas you see that had very little effect at all on the polarization. And again, here's results of before and after, using data assimilation with respect to depth and with respect to snow water removal. So you can actually do relatively well. The circles, again, are the truth measurements. So these are some examples of point-based studies. As I said, there are some global studies that are larger scale studies I'm aware of. The things that I think are worth keeping in mind when we eventually read those papers is that there are a lot of different snow models being used. There are a lot of different land models being used. There are different forcing data that's being used. There's different radiative transfer models that are being used. So we're at the point now where every group that's writing a paper that's been looking at this has sort of been using a different combination of things in that block diagram, if you will. And so if you're trying to compare them and make sense out of, well, did this work better than that? We're still at the stage where it's a little hard to see, where things are going. And as I say, you want to try to figure out what do we know and what do we don't know. And once you figure out what we don't know, then you can sort of answer the question, well, how do we go answer those remaining unknown questions? I would say we're somewhere between these first 2 stages. The first stage is, let's just go try it, see what happens. If enough people try enough different things, you'll be able to see a picture starting to form. I don't think we're quite there yet. We're somewhere in between these 2 things. And if you got, later on, I think we'll be able to see a much clearer picture of whether radiance assimilation really works for snow or under what conditions it works and so forth. So I know I'm running low on time. I'm going to run through some of these pretty fast. This is my own personal take on remaining issues. It's not focused purely on radiance assimilation, although that's one of the major things I was keeping in mind. I would say, the fidelity of the snow models is one of the key areas that, of our current limitations are. And that's also, it's hard to separate that from having input data that's of sufficient quality to be able to drive the models. I mean, what good is it if you have this great, sophisticated snow model, but you don't have the data to actually take advantage of those features? Then you have the radiative transfer model. There are some really sophisticated ones out there, dense medium radiated transfer, that explicitly deals with the dense medium, but it's a very sophisticated model. It's not, you know, it's unlikely to be something that you can use operationally for example. So you're going to have to figure out ways of parameterizing it. The medium sophistication models, which is I guess what I would consider MEMLs to be, seem to do a pretty good job of reproducing brightness, temperature, signatures, for example. But you do, that's only when you have detailed information about the actual snowpack conditions. You're not always going to have that. So we need to start looking at how fast do things fall apart when you start having more realistic quality data. And then there are some really simple radiated transfer models. Some people have been trying these. They only work for simple snowpacks. We only have those in certain places at certain times. So what else? There's certainly work that can be done with respect to optimizing of the assimilation, just like there is with folks doing assimilation for other things. But I think, at this point, there are bigger unknowns with the other stuff. So I'm not sure that, focusing on improving or optimizing the assimilation itself is going to really yield benefits as much as looking at improving the snow model and improving the radiated transfer model. I'll skip that in the interest of time. So here's my quick summary, and I actually put these in order, and it's just what I just said. I think actually the word snow, there should be, snow is missing from number 1. So the model of the snow, I think needs the most attention. Next is probably the radiated transfer portion of it. Not so much that you don't have radiated transfer models that aren't good, you got to find something that has the appropriate complexity or the appropriate fidelity, and then you have to think of it, also consider how you're going to get the ancillary data that's involved. As I said, there are some very sophisticated radiated transfer models, but you're never going to have the input data that they require. And in the assimilation framework that I showed, the radiated transfer model gets its input data from the snow model. So if your snow model is spitting out poor output, then your radiated transfer model's got no hope. And that gets back to some of this, this input data. And then last, as I said, optimization of the assimilation itself. So what's holding us back? I would say that, again, because my own personal feeling is that these guys are the most important, or the places that need the most help, is the lack of actual data that you can use to address those problems. And the ideal data that you would want is coincident, microwave observations with snow ground truth. Not at a global scale, but at a small enough scale where you can actually afford to do the detailed ground truth. So to me, this is really still where the focus needs to be for the time. And I'll skip some of this stuff here. So I took I made an attempt to describe what I would consider to be sort of an ideal validation data set. Of course, it's ideally you want everything. You want a lot of samples within each grid cell. Each of those samples needs to be high accuracy. You want wide geographic coverage. You definitely want to cover all the snow types, different terrain types, forest cover, and so forth. And you want it as often as possible. And of course, you're never going to get that. So what's acceptable? Well, it would be really nice to have a few cells where you have more than one sample data within the cell. That happens very rarely, unfortunately, with validation data sets. And then at least let's get some representative geographic coverage. We've got very, very limited data sets that have that coincident microwave and snow ground truth. And they only cover one or two kinds of snow, one or two times. So it's really not a lot to work with. So we've done, so as I said, Mike Duran, Steve Margulis, and Noah Wallish and I have had a little bit of NASA funding to attack this problem, and we were able to do one very small campaign, just 4 days at Steamboat Springs. This is the Storm Peak lab up here. So we set up a microwave radiometer, and we had a roped off area so that the skiers weren't going through there and disturbing our snow. And then we made measurements for 4 days. We tried a bunch of different techniques for getting the in situ, the actual snow ground truth. And then finally, at the end, we actually excavated the actual spot that the radiometer was looking at and did detailed ground truth right there. And part of this experiment was to look at different techniques for characterizing the snow path. What's the best way of, density is temperature is easy. You take a thermometer and you stick it in there, right? There's no problem there. Density is also relatively easy. You put a standard sampler in there of the known volume and you weigh it. Right? That's not too hard. But as I mentioned before, the thing that's microwave sensing is really sensitive to is grain size. And how do you get that? And it's not just the grain size, it's that there's a distribution. If you take a block of snow, not all the grains in there are going to be the exact same diameter. Some are bigger and some are smaller. There's a distribution, and the microwave radiative transfer is sensitive to that. And it isn't just the size of the grains, but it's how close they are and how they're distributed spatially within the snow volume. Well, how do you do that? So there's in the last few years, people have been developing techniques using like infrared photography, using contact spectrometers that you slide up and down the face of the snow pit. Very, interesting techniques. We tried 4 of them together to see which ones worked well, which ones worked better, and how well they match each other. And our truth was this technique called it's snow casting. So it turns out that some of our colleagues in the past have figured out a way to literally preserve a sample of snow. So you dig a hole, you cut out a block of snow, you stick it in one of our Chinese takeout containers, which are the government's cheap snow sample container, and then you pour dimethyl phthalate chilled dimethyl phthalate into the snow matrix, so it fills all the air pore space in there, and then you freeze it. You freeze the sample. So basically what that means is driving down into the village of Steamboat Springs and cleaning out all the grocery stores and all the dry ice. So like 300 pounds of dry ice in our vehicle. Anyway, we had several dozen of these samples. You pack dry ice in there. You seal these coolers. You can see the coolers that we had to drive up or have transported up the side of the mountain. And then we shipped them off to our colleagues at CREL, the Cold Regions Research and Engineering Lab up in New Hampshire, where they have the facilities for slicing these and then taking photomicrographs, and then we can analyze the snow grain sizes and spatial response. So there's actually a blog that was associated with that. And I'll stop here because I know we're out of time. If people want to hear about missions, I can go into it later.
Great, thank you.
Ed, so on the satellite footprint scale, how do you handle the large scale topography, like the rockets, stuff like that? How
We don't.
Fair enough.
You apply the same algorithm for a pixel that's
Just flat.
non-mountainous, right? Yeah.
Because the snow is always kind of mostly now.
Yeah, I mean, if you're dealing with a pixel that's several dozen kilometers in size, and you
Right.
go to a mountainous area, you've got all of this within
Right.
your pixel.
Right.
So you've got huge variation in the depth of the pack and the temperature, depending on whether it's facing this way or facing that way.
Right.
Forest cover, there's all kinds of variables. We ignore it. We can't do it. We have no, the traditional retrieval algorithm doesn't have the capability of dealing with that sort of stuff. Radar might. because you can get down to a smaller spatial resolution, but you
Right.
need to get to something like 100 meters.
Right.
You can do that with SAR, and that's what all the snow satellite proposals that are in here. So this is the NASA one, the SCLP, and this is the European one, the Core H2O, and they're talking about 100-meter resolution with radar. But radar algorithms are not very mature, and they're noisy.
But
So-
then at the point of scale, that the small scale roughness in the, in the underground.
You mean microscale roughness?
I mean the land surface. Will that play a role too?
Sure. But we don't have again,
Right.
unless we get down to a much finer spatial resolution, we don't have any great way of really dealing with that.
Please.
An even harder question, how do you deal with effective scale of snow grain size relative to a passive microwave scale pixel and the corresponding snow grain size in your model for the regional and global
Oh.
scale assimilation?
So you mean the fact that there's sub-pixel heterogeneity?
Even more so than terrain.
Yeah.
Yeah. So
Yeah,
how do you
so-
handle that?
We don't.
Okay. I was afraid that was right.
Yeah. I mean, the only way that grain size variability is addressed right now, so I'm talking about non-assimilation retrievals, right?
I'm talking about the
Traditional
studies that are in review.
Oh. The studies that are in review are using land models that have a resolution that's better than a passive microwave footprint. So they're looking at, in theory, they could do that kind of an experiment. How much better they can do. The problem is that it's sort of, you'd have to do it over a contiguous area in order to sort of be able to say, well, we compared it to what a passive microwave satellite would see. That's a lot of area here.
Yeah.
There are very, very few field studies where they've gone on that. You have to, practically speaking, you can only do that with microwave measurements if you have an airborne microwave instrument. And so there's very, very few cases where folks with the right airborne instrumentation and the aircraft and the ground truth have been able to go out and do that. I mean, the CLPX campaign, the big NASA thing, that was millions of dollars. And of course, they did it. I mean, they did a really big campaign because they had the DC-8, they had the P-3, they had the NOAA Aero Commander, and they had 4 different aircraft, 60 people on the ground for 3 weeks. You don't need to do all that, but you still need one aircraft or one set of microwave instruments on the aircraft. You still need to cover the ground truth over, one equivalent passive microwave pixel. It's logistically difficult to cover that much area.